Annex D example Durner possibly predates Rule 440.3b because the 1999 National Electrical Code, NEC, was the first edition of the NEC to contain Part Roman III. Annex D. Rule 440.3b was first introduced in the 1993 NEC. The hermetic nature of room air conditioners is not relevant to whether they are subject to the requirements of 430.24. Rule 440.3b specifically states that hermetic room air conditioners are subject to the requirements of 430.24. Therefore, a rule should be found indicating that hermetic room air conditioners are subject to the requirements of 430.24. Section 430.24 of the National Electrical Code addresses the several motors or loads on one branch circuit. It details the conductor requirements where two or more motors are connected to the same branch circuit. The intent of this section is to ensure that the conductors supplying power to multiple motors are adequately sized to handle the combined load. This helps prevent overheating and potential fire hazards. When sizing conductors for multiple motors on a single branch circuit, the NEC requires that the conductors have an ampacity equal to or greater than the sum of firstly, 125% of the full load current rating of the highest rated motor, plus secondly, the sum of the full load current ratings of all other motors in the group. This calculation helps account for the inrush current that occurs when motors start, which can be significantly higher than their normal operating current. By adding 25% to the highest rated motor, the code ensures that the conductors can handle the momentary surge of current without being overloaded. In addition to the motor loads, the branch circuit may also supply other loads, such as lighting or heating elements. In these cases, the ampacity of the conductors must be sufficient to carry the combined load of all motors and other appliances connected to the circuit. The NEC provides guidelines for calculating the ampacity of conductors based on their size, insulation type, and ambient temperature. It is important to select conductors with an appropriate ampacity rating to ensure safe and reliable operation of the electrical system. The overcurrent protection devices, such as circuit breakers or fuses, must also be sized appropriately to protect the conductors from overloads and short circuits. The rating of the overcurrent protection device should not exceed the ampacity of the conductors it is protecting. This ensures that the circuit will be automatically disconnected in the event of an overload or short circuit, preventing damage to the conductors and equipment. It is crucial to follow the guidelines and requirements outlined in the National Electrical Code when designing and installing electrical circuits with multiple motors. Proper conductor sizing and overcurrent protection are essential for ensuring the safety and reliability of the electrical system. Failure to comply with these requirements can result in overheating, damage to equipment, and potential fire hazards. Annex D of the NEC provides examples of calculations for various electrical systems, including motor circuits. These examples can be helpful in understanding how to apply the code requirements in practical situations. By referring to Annex D, electrical professionals can gain a better understanding of how to size conductors and overcurrent protection devices for multiple motors on a single branch circuit. Rule 440.3b clarifies that air conditioning and refrigeration equipment, including hermetic refrigerant motor compressors, are subject to the requirements of Article 430, specifically 430.24, when calculating the ampacity of conductors. This means that when sizing the conductors for an air conditioning unit or refrigeration system, the electrical designer must consider the full load current of the compressor motor, as well as any other motors or loads connected to the same circuit. The conductors must be sized to handle the combined load, in accordance with 430.24. This provision is important because air conditioning and refrigeration equipment often have high starting currents, which can place a significant strain on the electrical system. By requiring compliance with 430.24, the NEC ensures that the conductors are adequately sized to handle these high starting currents without overheating or causing voltage drop. In addition to conductor sizing, 440.3b also affects the selection of overcurrent protection devices for air conditioning and refrigeration equipment. The overcurrent protection devices must be sized to protect the conductors and equipment from overloads and short circuits, while also allowing for the high starting currents of the compressor motor. The NEC provides specific guidelines for sizing overcurrent protection devices for air conditioning and refrigeration equipment, taking into account the full load current and locked rotor current of the motor. It is important to carefully follow these guidelines to ensure that the equipment is properly protected and that the electrical system operates safely and reliably. The referenced Hermetic refrigerant motor compressors in 440.3b is significant because these types of compressors are commonly used in air conditioning and refrigeration equipment. A Hermetic compressor is one in which the motor and compressor are sealed in a single housing, which helps to prevent refrigerant leaks. These compressors are typically more efficient and reliable than open-type compressors, but they also have higher starting currents. By specifically including Hermetic compressors in the scope of 440.3b, the NEC ensures that the electrical requirements for these types of equipment are properly addressed. Overall, 440.3b is an important provision in the NEC that helps to ensure the safe and reliable operation of air conditioning and refrigeration equipment. By requiring compliance with 430.24, the code ensures that the conductors and overcurrent protection devices are adequately sized to handle the high starting currents and full load currents of these types of equipment. This helps to prevent overheating, voltage drop, and other electrical problems that could lead to equipment failure or fire hazards. The relationship between 440.3b and 430.24 is crucial for understanding how to properly size conductors and overcurrent protection devices for air conditioning and refrigeration equipment. Section 430.24 provides the general requirements for sizing conductors for multiple motors on a single branch circuit, while 440.3b clarifies that these requirements also apply to air conditioning and refrigeration equipment, including Hermetic refrigerant motor compressors. When applying these rules, it is important to firstly determine the full load current of each motor connected to the circuit, including the compressor motor. Secondly, calculate the sum of the full load current of all motors, with the highest rated motor multiplied by 125%. Thirdly, select conductors with an ampacity equal to or greater than the calculated sum. Fourthly, choose overcurrent protection devices that are sized appropriately for the conductors and equipment. By following these steps, electrical professionals can ensure that the electrical system for air conditioning and refrigeration equipment is properly designed and installed in accordance with the NEC. The history of these rules in the NEC is also important to consider. As mentioned earlier, 440.3b was first introduced in the 1993 NEC, while Annex D was first included in the 1999 NEC. This means that Annex D example donor may predate 440.3b, as the example may have been based on an earlier version of the code. However, regardless of when the example was created, it is important to follow the current requirements of the NEC when designing and installing electrical systems. The NEC is updated every 3 years to reflect changes in technology and industry practices, so it is essential to stay up to date with the latest edition of the code. In conclusion, understanding the relationship between 440.3b and 430.24 is crucial for ensuring the safe and reliable operation of air conditioning and refrigeration equipment. By following the requirements of the NEC and staying up to date with the latest edition of the code, electrical professionals can ensure that these types of equipment are properly installed and protected. The NEC provides comprehensive guidelines for electrical installations covering various aspects such as wiring methods, overcurrent protection, grounding, and equipment installation. It is essential for electrical professionals to have a thorough understanding of the NEC and to apply its requirements correctly in their work. Failure to comply with the NEC can result in electrical hazards, equipment damage, and potential legal liability. Therefore, continuous education and training are crucial for electrical professionals to stay informed about the latest code changes and best practices. In addition to the NEC, there are other standards and regulations that may apply to electrical installations depending on the location and type of project. These may include state and local codes, as well as industry standards developed by organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA. It is important to be aware of all applicable standards and regulations and to comply with them in all electrical work. Proper electrical design and installation are essential for ensuring the safety and reliability of electrical systems. By following the requirements of the NEC and other applicable standards, electrical professionals can help to prevent electrical hazards and ensure that electrical systems operate safely and efficiently. This not only protects people and property from electrical harm, but also contributes to the overall sustainability and resilience of the built environment. The National Electrical Code, or NEC, is a comprehensive set of standards and guidelines for electrical installations in the United States. It is developed and published by the National Fire Protection Association, or NFPA, and is updated every 3 years to reflect changes in technology, industry practices, and safety requirements. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, equipment installation, and special occupancies. It is intended to provide a minimum level of safety for electrical installations and to protect people and property from electrical hazards. The NEC is widely adopted by state and local governments, and compliance with its requirements is often mandatory for electrical work. Electrical professionals, including electricians, engineers, and contractors, must have a thorough understanding of the NEC and apply its requirements correctly in their work. Failure to comply with the NEC can result in electrical hazards, equipment damage, and potential legal liability. The NEC is organized into chapters, articles, and sections, each addressing a specific aspect of electrical installations. Chapter 1 covers general requirements such as definitions, scope, and administration. Chapters 2 through 7 cover specific aspects of electrical installations such as wiring and protection, wiring methods and materials, equipment for general use, special occupancies, and special equipment. Chapter 8 covers communications systems such as telephone, data, and cable television. Chapter 9 contains tables and examples to assist in applying the code requirements. Each article within a chapter focuses on a particular topic, such as overcurrent protection or grounding. The articles are further divided into sections, which provide specific requirements for the topic being addressed. The NEC uses a numbering system to identify each section, making it easy to locate specific requirements. For example, Section 310.15 addresses the ampacity of conductors, while Section 250.50 covers grounding electrode systems. The NEC also includes annexes, which provide additional information and guidance on specific topics. Annexes are not part of the enforceable requirements of the code, but they can be helpful in understanding and applying the code provisions. For example, Annex C provides examples of conductor calculations, while Annex D provides examples of building information modeling. The NEC is a complex and comprehensive document, and it can be challenging to navigate and understand its requirements. However, there are resources available to help electrical professionals learn and apply the NEC correctly. These resources include training courses, seminars, and publications offered by organizations such as the NFPA, the Institute of Electrical and Electronics Engineers, or IEE, and various trade associations. It is important for electrical professionals to continuously update their knowledge and skills to stay informed about the latest code changes and best practices. The NEC is constantly evolving to address new technologies and safety concerns. The NEC is an essential tool for ensuring the safety and reliability of electrical installations. By understanding and applying its requirements correctly, electrical professionals can help to prevent electrical hazards and protect people and property from electrical harm. The NEC is not a design manual, but it provides a framework for designing and installing electrical systems that meet minimum safety standards. Electrical design should be performed by qualified professionals who have the knowledge and experience to ensure that the system meets the specific needs of the application while complying with all applicable codes and standards. The NEC is also not a substitute for good workmanship. Electrical installations should be performed by qualified electricians who are trained and experienced in the proper techniques and procedures. Proper workmanship is essential for ensuring that electrical systems are installed correctly and operate safely. The NEC is a living document that is constantly being updated and revised to reflect changes in technology and industry practices. It is important for electrical professionals to stay informed about the latest code changes and to adapt their practices accordingly. The NEC is a collaborative effort, with input from a wide range of stakeholders, including electrical engineers, contractors, manufacturers, and regulators. The NEC development process is open and transparent, and all interested parties have the opportunity to participate in the process. The NEC is a valuable resource for electrical professionals, and it plays a vital role in ensuring the safety and reliability of electrical installations. By understanding and applying its requirements correctly, electrical professionals can help to protect people and property from electrical hazards and to promote the responsible use of electricity. The requirements of 430.24 and 440.3b are interconnected in the context of electrical installations, particularly when dealing with motor loads and air conditioning or refrigeration equipment. Section 430.24 of the National Electrical Code, or NEC, addresses the scenario where multiple motors or motor loads are supplied by a single branch circuit. In such cases, the code mandates specific guidelines for determining the minimum ampacity of the conductors feeding these loads. The primary intent behind these regulations is to ensure that the conductors are adequately sized to handle the combined electrical demand of all connected motors, preventing overheating and potential fire hazards. To calculate the minimum conductor ampacity, 430.24 prescribes a formula that takes into account the full load current ratings of each motor. Specifically, the conductors must have an ampacity equal to or greater than the sum of firstly 125% of the full load current rating of the highest rated motor, plus secondly the sum of the full load current ratings of all other motors in the group. This additional 25% applied to the largest motor is intended to accommodate the elevated inrush current that occurs when motors initially start. This inrush current can be significantly higher than the motor's normal operating current, and the conductors must be capable of handling this temporary surge without experiencing excessive voltage drop or overheating. Furthermore, if the branch circuit supplies additional non-motor loads, such as lighting or heating elements, the ampacity of the conductors must be increased accordingly to accommodate these loads as well. The NEC provides tables and guidelines for determining the ampacity of conductors based on factors like conductor material, insulation type, and ambient temperature. Choosing conductors with the appropriate ampacity is crucial for ensuring the safe and reliable operation of the electrical system. Complementing 430.24, Section 440.3b specifically addresses air conditioning and refrigeration equipment, including Hermetic refrigerant motor compressors. This section clarifies that the provisions of Article 430, including 430.24, apply to these types of equipment. In essence, 440.3b reinforces the applicability of the motor load calculations outlined in 430.24 to air conditioning and refrigeration systems. This means that when sizing conductors for an air conditioning unit or refrigeration system, the electrical designer must consider the full load current of the compressor motor as well as any other motors or loads connected to the same circuit. The conductors must be sized to handle the combined load, following the calculations specified in 430.24. The significance of 440.3b lies in the fact that air conditioning and refrigeration equipment often exhibit high starting currents, which can place a considerable strain on the electrical system. By explicitly stating that 430.24 applies to these systems, the NEC ensures that the conductors are adequately sized to handle these high starting currents without experiencing adverse effects like overheating or excessive voltage drop. In addition to conductor sizing, 440.3b also influences the selection of overcurrent protection devices for air conditioning and refrigeration equipment. The overcurrent protection devices must be sized to protect the conductors and equipment from overloads and short circuits, while also accommodating the high starting currents of the compressor motor. The NEC provides specific guidelines for sizing overcurrent protection devices for air conditioning and refrigeration equipment, taking into account factors like the full load current and locked rotor current of the motor. It is imperative to adhere to these guidelines to ensure that the equipment is properly protected and that the electrical system operates safely and reliably. In summary, 430.24 and 440.3b work in tandem to ensure the safe and reliable operation of electrical systems with motor loads, particularly those involving air conditioning and refrigeration equipment. Section 430.24 provides the general framework for calculating conductor ampacity for multiple motor loads, while 440.3b clarifies that these requirements apply specifically to air conditioning and refrigeration systems, emphasizing the need to account for the high starting currents associated with these types of equipment. By understanding and applying these code provisions correctly, electrical professionals can design and install electrical systems that meet the demands of motor loads and air conditioning equipment while maintaining a high level of safety and reliability. The application of National Electrical Code, or NEC, sections 430.24 and 440.3b is critical in electrical installations involving motors and air conditioning equipment. Firstly, understanding 430.24. This section is crucial when a single branch circuit supplies power to two or more motors. The main goal is to ensure that the conductors have enough ampacity to handle the combined load of all the motors, preventing overheating and potential hazards. The calculation involves two main steps. Firstly, identify the motor with the highest full load current rating. Secondly, calculate the minimum ampacity of the conductors. This is done by taking 125% of the highest full load current rating of the largest motor, and adding it to the sum of the full load current ratings of all the other motors on the same circuit. For example, if a branch circuit supplies 3 motors with full load currents of 10 amps, 8 amps, and 6 amps respectively, the calculation would be as follows. The largest motor is 10 amps. Then 125% of 10 amps is 12.5 amps. Then add 12.5 amps to the sum of the other motors, which is 8 amps plus 6 amps, which equals 14 amps. Therefore, the calculation is 12.5 amps plus 14 amps, which equals 26.5 amps. The conductors must have an ampacity of at least 26.5 amps. If there are non-motor loads on the same circuit, their current must also be added to the calculation. Now, understanding 440.3b. This section specifically applies to air conditioning and refrigeration equipment, especially those using Hermetic refrigerant motor compressors. It essentially states that the rules in Article 430, including 430.24, apply to these types of equipment. This is important because air conditioning and refrigeration equipment often have high starting currents, and 440.3b ensures that these are taken into account. This section ensures that when sizing conductors for air conditioning units, the electrical designer considers the full load current of the compressor motor, along with any other motors or loads on the same circuit. The conductors should be sized to handle the combined load as calculated per 430.24. Practical application. Consider an air conditioning unit with a hermetic compressor along with other motors connected to a single branch circuit. To correctly size the conductors, one must, firstly, determine the full load current of each motor, including the compressor motor. Secondly, apply the 430.24 calculation, adding 125% of the highest rated motor's full load current to the sum of the others. Thirdly, select conductors with an ampacity equal to or greater than the calculated value. Fourthly, ensure that the overcurrent protection is adequate, as per NEC guidelines, for the conductors and the equipment, accounting for the motor starting currents. Therefore, by following these steps, the electrical installation will comply with the NEC, ensuring safety and preventing electrical hazards.